So this says aldehydes and ketones can be oxidized by a peroxy acid. When those are oxidized by a peroxy acid, that's called the Baeyer-Villiger oxidation. So as you can see in this reaction, that aldehyde becomes a carboxylic acid. How the heck does that happen? Let's draw it. So aldehydes can be oxidized by peroxy acid. Note this is an O- of my peroxy acid, so I attack the carbonyl carbon. Like we've done so many times at this point, that peroxy acid gets attached to your carbonyl carbon. This could be MCPBA that you add. This is not MCPBA's structure, but we need it under slightly basic conditions to make sure that we get the O- version to attack the carbonyl carbon. Then we get this. This is not a stable molecule because this OO peroxide bond, OO, is explosive, not great. So let's break that OO bond. If we just broke it like that, that would leave this oxygen without an octet. That's not good. So this hydrogen can give his electrons to the oxygen. This is kind of like we're doing a hydride shift here to a carbocation, except this is oxygen that we're doing the hydride shift to, and we never officially form a carbon, we never officially form an oxygen without an octet. So it's like a hydride shift to the oxygen is what we're doing. We call this step a migration most of the time in this Baeyer-Villiger oxidation. So the hydride can migrate next door. That would leave the carbon without enough electrons, so the oxygen can fold back down to reform a double bond between the carbon and the oxygen, making us this product. So this carboxylate came from what was my peroxy acid. This hydrogen, we'll circle him in red. This hydrogen is this hydrogen. This hydrogen migrated and is no longer connected to the carbon. He is now connected to the oxygen. Hydrogen is not the only thing that can migrate in this way. The Baeyer-Villiger oxidation, if you oxidize an aldehyde, it's always the hydrogen that migrates. So if you oxidize an aldehyde, you always end up with a carboxylic acid. Always. But if you start with a ketone and you have two R groups, you need to know what kind of R group is on either side because some R groups migrate faster than others. Let me show you what I mean. Like I said, some R groups migrate faster than others, so that bottom box tells you who can migrate the fastest, and you see that H is the first on the list. So that's why aldehydes always become carboxylic acids, because H is the fastest migrator. Methyl is the slowest. Secondary and phenyl, that's benzene, the same. Tertiary is faster than secondary, which is faster than primary. Okay, kind of goes in order of carbocation stability-ish, but hydrogen is the fastest. So if we try and oxidize these ketones, we need to say what kind of carbon is it on this side of my ketone. That yellow highlighted carbon is my pH, is my phenyl carbon. The blue highlighted carbon on the other side is a primary. It's not primary right now, but imagine if it were migrating, it would be migrating as a primary carbon. You're not counting the carbonyl that it's connected to. You're just counting the number of carbons other than the carbonyl that it's connected to. So phenyl migrates faster than primary. So that leads us to that product. Whatever migrates faster ends up with the O squeezed between the carbonyl carbon and the thing that migrates faster. We start out with a ketone, we end up with an ester. In this bottom example, we've got this hydrogen, which is this carbon, which is a methyl carbon. And we've got this carbon, which is a secondary carbon. Again, we're not counting the carbonyl carbon. We're counting if it were migrating, what kind is it that is migrating? So secondary versus methyl, secondary migrates faster. So we end up with that ester. That wasn't a lot to say about the Baeyer-Villiger oxidation, but it's an important little reaction of aldehydes and ketones. Another important little reaction of aldehydes and ketones is the Wittig. It's a German thing, the Wittig reaction. The Wittig reaction works with this phosphorus type of compound, this thing right here. That's one way you can draw the phosphorus compound. There's a resonance structure of the same phosphorus compound. That phosphorus compound is known as an ylide. Y-L-I-D-E, ylide. So the ylide reacts with a carbonyl to form a C double bond C. Let's see how that works. You can draw the mechanism from either of the resonance structures of the ylide. You're just going to need more arrows, or your arrows are going to need to come from different places depending on which one you do. I'm going to draw it from the positive negative version so that I can see my negative carbon attacks the carbonyl carbon. And rather than folding up and making an O-, simultaneously, my pi bond is going to attack the phosphorus, the positively charged phosphorus. Remember, phosphorus is in period 3 of the periodic table, so it's a large radius thing that can accept more than an octet. And so at this point, phosphorus has more than an octet. There's my compound. I made a little square in the middle. Is that weird or what? So this square doesn't hang around for a long time. It falls apart to give you your product. It always falls apart that the oxygen and phosphorus leave together. Oxygen and phosphorus always leave together. And your carbon stays connected to your carbon, and you get a CH2 on your molecule. Do you always get a CH2? No. It depends on what was over here on your ylide. This group, that was a CH2 for this example, could be any kind of carbon-containing compound. So this one made a terminal alkene, but if we had had other stuff connected here, that other stuff would have still been connected here. The Wittig is a good way to make an alkene. It's very good at making terminal alkenes like this, but it can also make internal alkenes when you have a lot of branches on your ylide compound. This thing is an ylide. You need to know how to make an ylide. So let's walk through that next. So if I have an alkyl halide compound that is capable of being SN2'd, and I add triphenylphosphine, that's this thing, PPH3, triphenylphosphine. Phosphorus in triphenylphosphine has a lone pair. So that lone pair on my phosphorus can attack SN2 to give me triphenylphosphine connected to that benzene, that benzyl group. Let's see if we can draw it legibly. Benzene, CH2, PPH3. When PPH3 connects like that, he went from neutral to now having 4 bonds, just like nitrogen, his upstairs neighbor. He's got a positive when he's got 4 bonds. So then I add phenyllithium. Phenyllithium is a crazy strong base. So that crazy strong base takes a hydrogen from next door to the phosphorus. Why would it take a hydrogen from next door to the phosphorus? Because when it does so, it makes a carbon that has a minus next door to a phosphorus that has a positive. So you can share electrons between your carbon and phosphorus. That is my ylide. Well, let me clear off the screen so you can see it a little better. So there's my ylide, a little more clearly than it was previously. And I add a carbonyl containing compound. The big picture of what happens in the Wittig reaction, the PPH3 runs away with the O, and the carbons that each of those were connected to run away together. So these carbons, there's a carbon up here, and those carbons end up connecting together. I'm going to give it a shot drawing it digitally here. I drew it as a cis double bond, which is most likely when you do a Wittig reaction, but we won't get into stereochemistry specifics with this thing. What if I ask you to synthesize a molecule? What ylide and carbonyl compound are needed to make that alkene? And how could you synthesize the ylide and carbonyl from compounds 8 carbons or fewer? Note, PPH3 doesn't count. This also says do it from 6 carbons and fewer. We're going to try it. I should have shown this earlier, but the take-home message for a Wittig is cut off your oxygen, cut your ylide in half, and stitch together the pieces that weren't stitched together previously. Oxygen always runs away with phosphorus, like this. And you're going to make a new carbon-carbon bond, like this. You're just cutting those two things and stitching together the things that weren't previously stitched. Now let's try the synthesis. Wittig makes double bonds. So that double bond is what you're going to make when you're trying to do this from a Wittig reaction. So the two pieces are going to be these, except one of them needs to be a carbonyl, while the other is your ylide, like that. You could absolutely 100% reverse the order. This could be your ylide, and this could be your carbonyl. It doesn't matter. One is not really preferred over the other. It just depends on how you want to make it. The next question was, how would you synthesize your carbonyl and ylide from compounds 8 carbons or fewer? So if we wanted to try with the blue one, we need to synthesize this thing. It doesn't actually tell us rules. I should have made up rules. How about synthesize this from an alkane, just to flex and show that we can? I'm going to make it from this 6-carbon alkane, actually. So starting the synthesis in the forward direction, every alkane ever, the only reaction that they do is radical stuff. Make a halogen. If you do BR, it's selective, so it goes to the armpit and the armpit only. And then I can maybe do some Kotbu to do selective elimination over here. E2, anti-8F, give me elimination over there. Then I can do boron stuff, BH3, hydroxide, and peroxide to give me an anti-Markovnikov alcohol. And then from there, I want that alcohol to become an aldehyde. So I need a weak oxidizing agent. Chromium, pyridine, and HCl, also known as PCC. So that's my aldehyde made. It says make them both from 8 carbons or fewer. So I'm going to make it from, how about this alkene? They did not tell us what functional group we had to make it from, so how about this alkene? 8-carbon alkene. Starting from the forward synthesis details, alkene, let's make it HBr and peroxides. give me an anti-Markovnikov Br. Is that the only way to get an anti-Markovnikov Br? No. You can make it an alcohol and do a SN2 on it or something. Then I add some PPH3 so that I get this thing with a positively charged phosphorus. I add a strong base. How about butyl lithium? Strong base makes me get the C minus. Whoops. And the resonance form of the C minus right here is this double bonded ylide. Maybe I should draw the resonance form because I feel like y'all would want me to. Butyl lithium takes a hydrogen from that carbon there. We're going to call it the alpha carbon because it relates to what we're doing next. So we've talked about two small reactions of aldehydes and ketones. Time to knock out one more. This may not be super familiar to you, but we talked about conjugated dienes a long time ago. And we said conjugated dienes always make two products. Even if you were trying to control equivalence, you're always going to get two products, but you can control how much percentage of one or the other you get based on time and temperature. We called one of these the kinetic product, and we called one of these the thermodynamic product. Do you remember who's who? The kinetic product was favored at low temperatures and short reaction times. The kinetic product is not as stable as the thermodynamic. So this product is kinetic because it's higher on my energy diagram. This product is thermodynamic. It's lower on my energy diagram. We went into a lot more detail then, and we're not going to revisit all of that now. But I was trying to make you remember 1,2 addition versus 1,4 addition because it's relevant for what we will talk about here. There's a carbonyl compound, and that carbonyl compound has an alkene in the same molecule. If you drew resonance of this carbonyl molecule, you would get a single bonded oxygen with a minus, a positive on the carbon, and the alkene down there. Can that alkene get involved in the resonance? No. So that resonance that I've drawn is the only resonance for this guy. Is it any different for this guy? Uh-huh. I can draw resonance where I have a single bonded oxygen, a minus, plus down here on what was the carbonyl carbon, just like the one above. But this time, I can have more resonance where that alkene gets involved also and have a positive down there. So I have a positive on two positions, here and there, here and there. Because of resonance, there are positives in two positions, partial positives in two positions. What's so different about the top alkene, or the top carbonyl and the bottom carbonyl, and the position of the alkene? The bottom one is conjugated, and because it's conjugated, you have a partial positive in a couple of spots. The conjugated carbonyl has a more single bond character because out of 3 resonance structures, 2 of them have the CO as a single bond instead of a double. And like I have already said, there are 2 sites for nucleophilic attack. You get different products based on the style of your nucleophile. What do I mean? CH3Li gives you one type, one style of product, while CH3SH gives you a different style. We're going to draw it, but before we do that, let me talk about the words. So if you attack the carbonyl, that's called direct addition. Directly attack the carbonyl. Things that do direct addition are strong nucleophiles, things that add irreversibly. As we walk through the mechanism, that will make a little more sense, I think. But strong nucleophiles that add irreversibly add 1,2 direct addition kinetic product. What kind of things are strong nucleophiles that do 1,2? Fast and furious nucleophiles. What nucleophiles are fast and furious? Hydride donors, like lithium aluminum aluminum hydride, sodium borohydride. Hydride donors are irreversibly added. Organolithiums are crazy, fiercely strong reagents. They add irreversibly. We're going to say that Grignards also add irreversibly, but there's a little bit of reversibility to a Grignard addition, but we're going to ignore it for now. If you're not on the list of fast and furious nucleophiles, we will call you a slow and patient nucleophile. You will make the more stable thermodynamic product. Anything that's not fast and furious, we will call slow and patient, and we'll get the thermodynamic product out of it. Let's look at the examples with methyl lithium and methane thiol. So when you recognize that you have a conjugated carbonyl that needs to react, you have to ask yourself, is the nucleophile I'm adding fast and furious? CH3Li is fast and furious. So you attack the carbonyl carbon like this. And then you protonate the O- you made. That doesn't seem new. That doesn't seem creative. That doesn't seem different from anything we've done previously. So why the heck are we talking about it? When the nucleophile is fast and furious, it is not different from what we've been talking about. This is called direct addition because your nucleophile is fast and furious. Attack the carbonyl carbon, be done. Nucleophiles that are slow and patient, aka the not fast and furious nucleophiles, they can add to the carbonyl carbon like this. But that kind of intermediate, meh, it could fold down and kick out to lead you right back where you were. Because kicking out an S is very easy to do. Is kicking out a methyl group, if we were to fold down and kick out a methyl minus, no. But kicking out an S is kind of easy, so we can fold down and kick out. This reaction is reversible. Because it's reversible, it can add, get kicked out, add, get kicked out, add, get kicked out many times. But remember, conjugated carbonyls have two sites for nucleophilic attack, two sites that are partially positive. So this sulfur can also attack down here because he's slow and patient and can wait around for the positive charge to be ready for attack down there. So comparing these two partial positives, this one's a greater partial positive, this one's a lesser partial positive. Slow patient nucleophiles can attack the lesser partial positive. The fast and furious ones, they attack the first available positive no matter what. So I get here, and some base comes to clean up. And I get this thing. Well, this thing, that looks interesting and strange. I can draw resonance of this thing. The resonance makes a C minus out here instead of an O minus. This is sometimes referred as the oxyanion, and this is the carbanion. On this magical thing called an enolate. This thing is an enolate. And in coming videos, you'll hear me say that word again and again and again. Enolate, enolate, enolate. Again and again and again. But for now, I'm just introducing you to what it is. The oxyanion version of an enolate is more stable than the carbanion version because of negative on most electronegative. But it's kind of easier to see how the carbanion version turns into what's my predicted final product. Some H in solution, it's probably an H off of another sulfur thingy. Some H in solution protonates my carbanion version, and I get this. If I had protonated the oxyanion version without drawing the mechanistic arrows, here's what I get. This is an enol, and enols tautomerize to their keto version. So this is my final predicted product if I react with methane thiol. This is conjugate addition. This is the product of conjugate addition. So up here in orange, direct addition. Down here in purple, conjugate addition. If we summarize a quick wrap-up, depending on the style of your nucleophile, you may get direct or you may get conjugate addition. If you have a fast and furious nucleophile, remember those are hydrides and organometallics. Fast and furious nucleophiles give you direct. They do not patiently wait around for the positive to form. Conjugate addition happens with slow, patient nucleophiles that can wait on the positive to form. The direct product is the kinetic product. The conjugate addition is the thermodynamic product. Why? If you remember from that last set of slides, that last couple of pictures I showed, we said the thermodynamic product is the more stable product. This alkene is di-substituted, so it's more stable because it's di-substituted. This one is a mono-substituted alkene. If you look at our alkenes here, this is a tri-substituted alkene. This is a di-substituted alkene. It follows the same pattern. Lower substitution, less stable product, kinetic product. More substituted, more stable product, thermodynamic product. Okay, one final thing for our big picture. In the end, because this is our final product, in the end, it simply looks like the sulfur reacted with only the alkene. In the end, it looks like the methyl lithium reacted with only the carbonyl. So these products are confusing to students sometimes because it looks like the two functional groups reacted independently. This orange did act independently of the alkene, but the purple, the reversible one, did not act independent of the alkene. The final product looks like it acted independently of the carbonyl, but it didn't. Because of tautomerization in the end, it looks like the alkene was all that's involved, but it's not true. Be wary. We're not switching back to the slides because what comes next is a bunch of examples. Note, this is an alpha-beta unsaturated carbonyl. This is alpha-beta unsaturated carbonyl. Alpha-beta unsaturated carbonyls, conjugated carbonyls, when you have a nucleophile that's going to react with them, you must ask yourself if that's a fast and furious nucleophile or a slow and patient nucleophile. I encourage you to pause the video and attempt these on your own, because if we were in class, I would certainly make you do it. Nevertheless, here we go. Are you confident about any of these being fast and furious or slow and patient? Hopefully, you're confident that lithium aluminum hydride is fast and furious. It's going to react with the carbonyl and the carbonyl only. Rather than drawing a whole mechanism, there is my product. Hopefully, you are also confident that an organolithium is a fast and furious nucleophile. Rather than drawing a whole mechanism, I'm only drawing the product, and it's that. Here's another lithium-containing molecule. Is it fast and furious? No, It's slow and patient. We're going to say that Grignards can do direct addition, fast and furious addition, but organocuprates are weaker than Grignards. Grignards truly give you a little bit of both direct and conjugate, but organocuprates give you all conjugate addition. One more problem that students have with conjugate addition, especially with cuprates, there are 2 methyls here and they want to add 2 methyls, but no, one of those groups gets added, not both. Conjugate addition. That's it. Amines are also slow, patient nucleophiles. Conjugate addition. Ta-da! HBr. Conjugate addition. Students sometimes start with this one on their own, and they want to predict this as the product. And I say, that's not the product. Even if you were trying to do old reactions, old knowledge, HBr to an alkene, old knowledge, this still should not be your predicted product, because carbocation here versus carbocation there, carbocation here is bad news because it's next to an electron withdrawing group. So carbocation here, even though it's tertiary, is less stable than carbocation here that's secondary. That electron withdrawing group makes a big difference. So this is the wrong product. It would have been the wrong product even a long time ago when we were learning about Markovnikov. That is all.